This tutorial will demonstrate Monte Carlo computations. First of all, we need to get some molecules. Let's go and get a box of water molecules, and we'll make this box 10 angstroms by 10 angstroms by 10 angstroms, just to be a reasonable size. So here's a box of water molecules with periodic boundary conditions. We're going to do Monte Carlo sampling of these water molecules to compute various things that we might along the path of that sampling. We can compute average bond angles, for example, which is a simple thing that we can do. We can compute heat capacities and enthalpies and so on and so forth. But let's just show you how this works. We go to Monte Carlo. It's really very simple. We have a random number, a seed that initiates the random number generation. We'll get different random number sequence with different seeds. We have a maximum displacement for a Monte Carlo jump of 0.05 angstroms. The smaller that is, the more the steps will be accepted. The bigger it is, the more rejections we'll get in the Monte Carlo sampling. We could heat or cool this, but we're just going to go ahead and just run it 100 steps. And here's the temperature. We're going to have a Boltzmann distribution generated corresponding to the 300 degrees. We can not look at every step, but do this with multiple steps and so on and so forth. But let's just look at this and go ahead. So the other thing I didn't explicitly discuss was which method we're using to do these computations. These are moving along relatively slowly because I'm recording it, but that was 100 steps, and we were actually using molecular mechanics. I think we were using amber force field, and the parameter set was amber 99. We have to choose when we do this some computational methodology, some computational engine, and we were doing that with an amber force field. Now that's how to do the actual sampling. If we wanted to average something along the way, let's take any water molecule. Let's take this one, select an angle, and we'll name that and call that angle, for example. And then when we go to do the Monte Carlo sampling, we can tell it that we want to do some averages. And specifically, it knows about angle because we defined angle. We could do it with potential energy, total energy, kinetic energy. Well, we don't have really kinetic energy here, but in any event, we'll average that angle, and we'll not only average it, but we'll plot it as well. And so away we go. Just tell it to go again. And this time, during the sampling, we get a plot of the why is it stopped? I don't know. It was doing something that I don't know what it was doing. Why did it stop for a while? The computer was doing something else. I don't know. Anyway, so there's the average, or there's the angle of that water molecule during the sampling. The angle went from 100 degrees to 109, and in the middle somewhere is the 105 degrees that represents a water molecule, except it is a stochastic value here that is the sampling at a particular temperature. If we go back in here and ask to see the average, this is the previous average, or the average we just took. So 105.3 degrees was the average angle in that water molecule during that sampling. So anyway, that's the way to do simple Monte Carlo calculations. There's lots of other facets of this, of course, if you really get into the theory of Monte Carlo, but basically doing simple Monte Carlo is simple.